1.2 is conditional statements. A logical inference or deduction is when we reason from a hypothesis to a conclusion. We would like to be able to say that if one thing is known to be true, then we can deduce the truth of something else. If we have the P and Q as the statements, a sentence of the form if P then Q is denoted symbolically by P arrow Q. P is called the hypothesis and Q is called the conclusion here. So here, if P, then Q, and we're going to call the P part as the hypothesis, and we're going to call the Q part as the conclusion. If you look at this example that I copied here, the sentence is, if 576 is divisible by 12, then 576 is divisible by 3. So the first portion of this sentence, which is the 576 is divisible by 12, this portion is called the hypothesis. And the second portion, which is 576 is divisible by 3, is the conclusion. So the notation is P then Q shows that this arrow is a connective, just like and or that can be used to join statements to create new statements. In order to define P then Q as a statement, we need to learn its truth values, just like the or and the and connector. So when you have the P then Q, let's just go ahead and look at its truth table, just like we looked at the truth table for and or. So for if P then Q, the only time you're going to get a false result will be when the hypothesis is true, but the conclusion is false. And there are very nice examples with daily life situations. How come the truth table for if P then Q only produces a false when the hypothesis is true, but the conclusion is false on the internet? So feel free to search some real-time examples. So when we look at the definition here, if P and Q are statement variables, then the conditional of Q by P is if P then Q, or P implies Q and is denoted by P arrow Q. It is only false when P is true and Q is false. Otherwise, all other situations, they will give you a true statement. So if the hypothesis is true, conclusion is true, and then this P then Q will be true. If the hypothesis is false, but the conclusion is true, P then Q will be also true. If hypothesis is false and the conclusion is false, then P then Q will be true. The only time you're going to get a false result will be when your hypothesis is true, but your conclusion is false. So here we're going to call the hypothesis, the P is the hypothesis, and Q is the conclusion, or you can use the other names for these two variables if you like. So let's look at this mathematical explanation here. So the statement is, if 0 is equal to 1, then derivative of sine of x is equal to e to the power of x. So this is a statement. So we don't know whether this is true or false yet, but this is a if P then Q situation. But let's think. This is going to be a true statement because of the truth table of P then Q situation. So the hypothesis 0 equals 1 is false. So P is false. And then whenever the P is false, we don't really look at the Q anymore. Whenever the P is false, either case of the Q, the result will be true. Therefore, this statement, we're going to be true here, because whenever the hypothesis is false, P then Q situation becomes a true statement. So if we look at the truth table for P or not Q, so this is the hypothesis, P or not Q, then not P. So let's look at the truth table for this statement. So here is the P and here is the Q. So Our conclusion is first, we're going to find the truth table for P or not Q. So this is my P. So first of all, I need to get not Q, since this is the truth. This is Q. So not Q will be just the opposite of these true or falses. So this is my not Q, and this is my P, and we want to OR the P and not Q. So the OR only becomes a false whenever both of the variables are false. So in this case, the third line is the only time that we're going to get a false after this OR statement. So for this P or not Q, we will get true, true, false, true. Now finally, we can focus on P then Q situation. So this is the hypothesis. So we're going to look at the conclusion. So whenever these are true, true, we want to look at the truth table here. So this is the hypothesis, and not P is the conclusion. So true, false. When the hypothesis is true, but the conclusion is false, that is false. When the hypothesis is true, conclusion is false, it will be false. Whenever the hypothesis is false, conclusion is true, then it will be true. Whenever the hypothesis is true, conclusion is true, then it will be a true here. And this is the truth table for this statement here. If we look at another example here, which says, we want to prove that if P, then Q or R is logically equivalent to P and not R. So this is if P and not R, then Q. So first of all, we're going to create the truth table for the left side. So the left side is if P, then Q or R. So we have three variables, P, Q, R, and then we can list the trues and false for P's. We can list the trues and false for Q, and we can list the trues and false for R. So first, we want to find the Q or R. So that really becomes false, Q or R. It only becomes a false when both of them are false. So the fourth and eighth line is the only time when both Q and R, they are false. So now I am back to if P then Q or R situation. So this is the hypothesis, this is the conclusion. So hypothesis is true, conclusion is true, so the result is true. Actually, all these three are the same thing, so they're going to be true. Now, hypothesis is true, but the conclusion is false, so this is going to be false. And whenever the hypothesis is false, regardless of the conclusion, we're going to get true in our logical table. Now, this is the left side of this problem. Here is the right side of the problem. The right side of the problem is if P and not R, then Q. Again, we have the PQR, and we need the not R, and we need the P and not R, which is going to produce the hypothesis. And this is the conclusion, and we're going to come up with the truth table. So here is the R. So these are not R. So if you look at the truth and false for P and not R, P and not R only becomes a true whenever both of them they have the true. So P and not R, this is P, this is not R. Both of them are true on this line. Both of them are true on this line. And that's all for the hypothesis section. Now, this is the hypothesis for if P, then Q. So Q is the conclusion. Now, whenever the hypothesis is false, we know that this if P, then Q will result true. So this is going to be true, this is going to be true, this is going to be true, and all these falses will be true. But now we have to look at these truths but in a closer direction. Whenever this is true, but the conclusion is also true, that's a true case. Whenever the hypothesis is true, but the conclusion is false, this will be the only time we're going to get a false in our truth table for this statement. Now, this is a very important fact in discrete math that we must be very, very comfortable with. We can prove this using the truth tables, but we're just gonna use this fact from now on. Whenever we see this statement, if P then Q, this is logically equivalent to not P or Q. So whenever we see if P then Q, we have to say that not P or Q. We need to know that they will be always logically equivalent. So let's look at some sentences here. The question is, can you rewrite this sentence in if-then form? Either you turn in your homework on time or you will incur a penalty. So if we use this rule for this sentence, if not P, you turn in your homework on time, and we're going to let the Q to be you will incur a penalty. So not P will be you turn in your homework on time, and Q will be you will incur a penalty. The original statement we were originally given in this form. So this sentence was either you turn in your homework on time. So we have the not P because we labeled this as not P, or you will incur a penalty. Also, the statement is P is you do not turn in your homework on time. Then the equivalent if-then statement would be if you don't turn in your homework on time, then you will incur a penalty. So this is how the relationship between P arrow Q, it will have the same logical equivalence as not P or Q. Okay. We have seen that the conditional statement, if P then Q, is logically equivalent to not P or Q. Thus, we can negate a conditional statement by using the De Morgan's law. So here is if P then Q. Let's just negate this expression by using the De Morgan's law. So we're going to negate this, first of all, for if P then Q, we're writing its equivalence, which is not P or Q. Now, whenever we're negating it, we will take the negate of not P, which is just P, negate of or is just and negate of Q will be not Q. So P and not Q, P and not Q. This is how we can write the negation of this sentence. Write the negation of this sentence. If I jump in a swimming pool, then I will get wet. If I jump in a swimming pool, then I will get. So far what we know is whenever we have if P then Q situation, it means logically equivalent to not P or Q. But whenever we want to negate this conditional statement, the negating of this conditional statement will be P and not Q. So when we go back to this example, if I jump in a swimming pool, then I will get wet. So P is the sentence, I jump in a swimming pool, and Q will be the sentence, I will get wet. So this is a state situation that P then Q. P is if I jumping in the swimming pool, Q is getting wet. So the negation will be, we're going to apply this rule for the negation. So the negation will be I jumped in the swimming pool and I did not get wet. So we are going to change this to an and we're going to negate the second part, I did not get wet. So never forget that in discrete math, this will be very important to know if P then Q is the logically equivalent to not P or Q, and its negation will be P and not Q. The logical equivalence of if P then Q and not P or Q is occasionally used in everyday speech. Here's one instance. Okay, so we're going to look at this example now. Application of the equivalence between not P or Q and P if P then Q. Rewrite the following statement in if-then form. Either you get to work on time or you are fired. So we're using this one. Either you get to work on time or you are fired. So not P is you get to work on time and Q is you are fired. Then the statement, given statement is not P or Q. Also P is, since this is a not P, you don't get to work on time. And the equivalent version of this is if you don't get to work on time, then you are fired. Because if P, then Q, right? If P, then Q. So since this part is not P, this part is Q, not P or Q. Since not P is you get to work on time, not P will be you don't get to work on time. If you don't get work on time, then you are fired is if P then Q equivalence version. Now we're going to look at contrapositive, converse, and inverse. So the definition of contrapositive of an implication is if P then Q is the statement not Q, then if not Q, then not P. So what's happening is we're switching the order and we are negating both of them. So this is called contrapositive. If not Q, then not P. A fundamental law of logic is that an implication is logically equivalent to its contrapositive. Like all other assertions that two statement forms are logically equivalent, this can be proved using a truth table. So here is an example. Write the contrapositive of this sentence. If I don't set my alarm, then I will miss my class. So for contrapositive, first we're going to switch the order and we're going to make both of them negated. We negate each component and reverse the order. So I don't miss my class. If I don't miss my class, then I set my alarm. So we're changing the order and we're negating both of them. So this is an example of a contrapositive situation. Definition. Now we're going to look at the converse and inverse. If we have this conditional statement, if P then Q, the converse will be if Q then P. So there is no negating this time. If Q then P is the converse. And the inverse is not P, if not P, then not Q. Here are some other important facts about converse and inverses. A conditional statement and its converse are not logically equivalent. A conditional statement and its inverse are not logically equivalent. The converse and the inverse of a conditional statement are logically equivalent to each other. So the converse and inverse, their truth table, they are logically equivalent to each other. And then remember contrapositive and the fundamental law of logic says that implication is logically equivalent to the contrapositive. There are other forms of the conditional statement. All of the following are same thing as if P then Q. So they can just show it as P arrow Q, or they can say if P then Q, P only if Q, P is a sufficient condition for Q, Q is a necessary condition for P. They all other forms of this conditional statement. Finally, we're going to look at the biconditional. Its definition is given statement variables P and Q, the biconditional of P and Q is P if and only if Q is denoted by this bidirectional arrow button. This means P if and only if Q. It is true provided P and Q have the same truth values, and also if P and Q have opposite truth values. The words if and only if are often abbreviated as EIFF. So this means if and only F. And if you look at the truth table for biconditional, they both have to have the same status. If they are both true, then it is true. If they are both false, it is true. But if they have different status, biconditional will give us a false result. Now, when we look at this, the truth table showing that P, if and only if Q, is logically equivalent to if P then Q and if Q then P. So if you look at the truth table, these are our P's, these are our Q's. Let's look at this one first. If P then Q, true and true is going to give us a true. True and false is going to give us a false. And these two cases will give us a true. So this is if P then Q. Now we're going to look at if Q then P. So these are the Q. Second one and fourth one is going to give me truth. First one is going to give me a true. Only the third one is going to give me false here. So this is the truth and false for if Q then P. Now we want to end these two columns. For end, it will be only true when both of them are true. So it is true on the first line and last line. So the second and third will be false. So this is the result for this part. So now if you remember the truth table for P, if and only if Q, they only become true if both of them, they have the same status, which is the first and the fourth line, and second and third will be false. And as we can see, they are matching here. If you look at an example for if and only if, so if you look at this sentence, direction says, rewrite the following statement as a conjunction of two if-then statements. This computer program is correct if and only if it produces correct answers for all possible sets of input data. So the solution will be, if this program is correct, then it produces the correct answer for all positive sets of input data. And if this program produces the correct answers for all possible sets of input data, then it is correct. Let's take a look at some summary statements from this lesson. So number one is, in an if-then statement is false if and only if the hypothesis is true and the conclusion is false. This is the only time an if-then statement will be false. The hypothesis is true, but the conclusion is false. The negation of if P then Q is, its negation is P and not Q. Because remember, if P then Q will be translated as not P or Q, so its negation will be P and not Q. The converse of if P then Q is, the converse means we're just going to change the order, if Q then P. The contrapositive of if P then Q is, if not Q then not P. The inverse of if P then Q is, if not P then not Q. A conditional statement and its contrapositive are logically equivalent. A conditional statement and its converse are not logically equivalent. R is a sufficient condition for S means if R then S. R is a necessary condition for S means if S then R. R only if S means if R then S. So these are some important summary sentences. Also, we're going to look at some extra practice here. When you have if P and then Q, this is only false when the hypothesis is true and the conclusion is false. If we give an example to this, if it rains, then the ground will be wet. So if it rains, which is true, but the ground is dry, the whole statement fails. Negation of if P and then Q. If P then Q is the logically equivalent to not P or Q, its negation will be P and not Q, meaning that P is true and Q is false. But for the converse, if P then Q, its converse will be if Q then P. If we look at the example of if it rains, the ground is wet, its converse will be if the ground is wet, it rained. When we look at the contrapositive, for contrapositive, if not Q, then not P. If the ground is not wet, then it did not rain. For the inverse, for the same example, if it does not rain, the ground is not wet. Always true. Sprinklers again. Conditional versus contrapositive. A conditional if P and then Q, and it's contrapositive, which is if not Q, then not P, are logically equivalent because you're switching the order and you're negating both of them. They will always have the same truth table. Conditional versus contrapositive. Conditional versus converse is not going to have the same truth table. Sufficient condition, we already talked about this. Being a square is sufficient for being a rectangle. If something is square, it is definitely a rectangle. For the necessary condition, having air is necessary for human life. If someone is alive, then they must have air. Only if you can drive, only if you have a license. If you are driving, then you must have a license. So when we have a converse, it flips to P and Q. Inverse negates both P and Q. Contrapositive flips and negates. Sufficient means enough to guarantee. Necessary means it is required. Only if the condition comes after only if. So I also have a diagram to explain the relationship between conditional, converse, inverse, and contrapositive. So the conditional is if P, then Q. Its contrapositive will be you are changing the order. So Q and P, they switch order and you're negating it. So contrapositive will be here. For converse, you're not changing the order. Oh, sorry, you're changing the order, but not negating them. If Q, then P. And for inverse, if not P, then not Q will be right here. Okay, again, conditional is if P, then Q. Contrapositive is if not Q, then not P. Converse is if Q, then P. And inverse will be if not P, then not Q. And when we look at the important takeaways, the conditional and contrapositive are always logically equivalent. The converse and the inverse are always logically equivalent to each other. This is all for 2.2.